In this video, I'm going to show how to do an iterated calculation in Mathematica to implement Euler's method to simulate the motion of a spring mass system, a simple harmonic oscillator. And just as we did in a previous video in MATLAB, I'm going to define some parameters and some step sizes and write down an iterated calculation to solve for the motion of the spring mass system. So I start as usual in a blank notebook and I will define some parameters of my spring mass system. Let's make the mass 2 kilograms. The spring constant will be 2 in SI units, and the damping value, well, we'll set it to a small value to begin with. And as I did in the previous video on MATLAB, I also will have to eventually define a step size. So I'm going to press enter here to evaluate these parameters. I'm also going to define a step size. I'll set it at 0.1 seconds to begin with. And I will now write down some code, some pseudocode, which is to write down the formula to update the position and velocity at a particular step. So I'm going to define that as being x0 and v0. And I'm going to write down a formula which updates those positions and velocities, position and velocity before the step has occurred, and update them to after that step has occurred. So that step is has an interval time of h. So if the original position is x0 and the original velocity is v0, then v0 acting for a time h changes x0 to x1 as so. And similarly, to update the velocity, I need to define v1 equals v0 plus a times h. The acceleration acts for a certain amount of time. So how are we going to put that into a function? Well, let's define a function called Euler Step. And Euler Step is going to take as an argument, it's going to take an x0 value, and it's going to take a v0 value, an initial position and initial velocity. This is, of course, these are meant to represent at any particular step n. And I'm going to write an equal sign here, and I'm going to say x0 plus v0 times h, and I'm going to have v0 plus a times h, where a is the acceleration. So the return value of this function is this expression. So this is x1 on the left and v1 on the right. Now if I evaluate that, you can see that Mathematica has immediately substituted in the step size 0.1, which is actually not what we want to have occurring, because if we wish to change the step size a little bit later, this Euler step function has already been evaluated. You can just ignore that. That Euler step function has already been evaluated. So what we'll do is we'll quit the kernel, and I'm going to change my definition of the Euler step function, and I'm going to write it with a colon. And what this means is that when I evaluate, when I define this function, when I ask for this function to be calculated, it will use this expression, but only at that time will it evaluate what h and a are, which allows them to change. So this is what's called a delayed evaluation. So colon equals performs a delayed evaluation. So I'll go back up here and I will define mk and b and h, and I'm not going to use this line. I'm going to delete that now, and I'll define Euler step as a delayed evaluation. And you can see that what's missing here actually is the acceleration. So if I were to type Euler step of some given position and velocity at a given step, at a given point in the simulation, let's just say it was 1.3 and minus 0.2, for example, then the result is the position and velocity after that step, but of course I've not yet defined the acceleration. So let's do that. I'm going to define the acceleration, and of course the acceleration at any given time is equal to minus x 0, it's equal to k times x0, k times x0 over m minus b times v0 divided by m. So that's all the physics of the problem. Right? So all the physics is encapsulated in this value a. But of course a is changing from step to step. So I need to put this expression and substitute it in where a appears in this formula. I'll just put that in brackets to make it a little bit clearer. There we are. I'll take away the semicolon. So I've now redefined the Euler step function. So remember, the Euler step function is calculating a single step of Euler's method, a single step in that integration. And now if I apply it, of course I've already defined m, k and b above, then I have calculated one step, and maybe it looks right, about right. So I'll delete that line of code there. Now I'm ready to save this notebook. I'm going to call it Euler example or something like that. NB meaning notebook. And now I would like to carry out this simulation for a certain amount of time. Well, let's define the amount of time I wish to calculate for. Let's say that's 20 seconds. I'll evaluate that with the enter key. I will now therefore need n steps where n is equal to t divided by h. So I can now use nest list to, if I call the help up for nest list, using Command Shift F on OS X, and I think it's F1 or Control H on Windows. You can see that what I want to do is I want to take the Euler step function and I want to apply it to an initial condition, and I want to apply that n times. This is why I've defined the input values as a list like this. This makes it a little bit simpler because I don't need to supply two arguments. I can simply supply one argument. So I can now just write Euler step as my function that I'm applying, and then this single argument is a list containing two values which contains initial conditions. So let's make that 0.1, and just for a bit of variety make it minus 0.3 meters per second. And I want to apply that for n steps. So let's ask for that to be carried out. Now that's not working because it says a non-negative machine-sized integer is expected at position 3. Well, this is position 3, so it wants n to be an integer. And as you can see, it's recognizing that h is a floating point number. So even though t divided by h looks like an integer, it actually isn't. So I need to find the integer part of that. So that's integer part of t over h, and I'll see if that works. And of course this t over h might be very far away from an integer if t and h were appropriately defined. For example, if h was 0.15 seconds rather than 0.1 seconds. So you need to make sure that you define that appropriately. So hopefully now if I press enter, there we are, it's producing a set of values. So these are the position and velocity at successive times. So I'll call that Euler data. Okay, so Euler data is a result of applying, let's put a semicolon on the end to suppress the output because it's a little bit long. And if I just do a list plot, now because this data is being returned as pairs of values where the first value is the position and the second value is the velocity, I should just be able to plot it. So I list plot it. There we are. So this is a so-called phase space plot. And a phase space plot, this horizontal axis here is the position, and the vertical axis is the velocity. So successive points are separated by h in time. In other words, 0.1 seconds as we have it here. So if I clean this up a little bit, let's make it joined goes to, it'll have a right arrow, press a space bar to join it up, make it true. Now I have a nice line. So because there is damping, and here is the damping value here, because there is damping, the trajectory of the particle is spiraling inwards. The particle is losing energy, the spring mass system is losing energy, and it's gradually progressing towards the origin where there is no energy at all. Now, let's see what happens when I change the damping to be 0. I will run everything again. So just for safety, I will redefine everything. And of course I don't need to calculate that particular step, but I do need to calculate the time, calculate the number of steps, do the simulation, and plot it. And it worked. So it's starting from, the initial condition was 0.1, and the initial velocity was minus 0.3. So this is our starting point here, actually, not over here. So you can see that one way of testing the code is we know that in the case where there's zero damping, there should be no loss of amplitude, which means in phase space that this trajectory should eventually close on itself. So actually we can spot that there's something funny going on here. The amplitude is actually increasing. We'll look at that in a bit more detail once we've cleaned up the code a little bit. I'm going to put everything into a single cell so I can execute it with a single press of an enter key. So I'll take that H and put it up here. I'll take the T and put it up there, and I'm just choosing to reorder my code so that I have all the definitions of the numbers at the beginning, and then I have all the calculations, in other words, a simulation, calculated below. So now I have a single cell. I can delete all the other cells. I'll just press delete, and I'll save the notebook. And now what I can do is I can just reevaluate everything with a single press of the enter key. Now what I'm going to do is reduce the value of h. And notice I'm keeping the total amount of time constant, so I'm still simulating the same physical system. I'm still simulating the same m, k, and b values. So when I press that, you can see that now that I've reduced the step size, the initial condition is the same, and the total simulation time is the same, so the endpoint should be in roughly the same place, but the algorithm has now been improved. There is less error, so the size of this ellipse, which represents the total energy of the oscillator, is more or less constant. I can show that a little bit better by reducing the step size still further, and you can see that with a sufficiently small step size, this ellipse is almost, but not quite, constant in amplitude. Okay, the trajectories more or less overlap each other. Now, this is a way of validating your simulation. As we saw in a previous video, we have a situation where we know that the size of that ellipse in phase space should be preserved. In other words, the amplitude of the oscillations is conserved because there is no damping. So we can now believe this simulation to some degree of accuracy. Now, of course, we haven't plotted versus time, but we saw how to do that in a previous video. What I'm going to stick with this phase space depiction, and what I'm going to do now is I'm going to keep the same small step size, a step size that's small enough that I can believe the accuracy of the simulation for this amount of time, and now I'm going to put some damping back in again. So I'll put a little bit of damping in, and I'll reevaluate it, and you can see that as I increase the amount of damping, let's increase it by a little bit more, that the particle amplitudes are now reducing as the time increases. So the particle trajectory in this phase space is a clockwise trajectory. If I increase the damping still further, you can see that as I do that, eventually the trajectory more steeply approaches the origin, and I can now simulate for a longer amount of time by increasing the total time of the simulation. It takes a little bit longer to calculate, but eventually it should give me a trajectory that gets very, very close to the origin, taking a little bit longer. Now, sometimes it will take a very long time to do this calculation, in which case you can abort it if you wish and just press by pressing Control dot or Command dot. Here it is. And so you can see that Mathematica has automatically rescaled these axes to try to show what it thinks you want to see more accurately, which is this interior location near the origin. So we can override that. Let's try and clean up the plot now. Firstly, we'll put a frame around the plot, and we'll say plot range goes to, I'm going to give the range of the plot Well, of course, we know what the x0 and v0 values are. Let's put those in explicitly. I'll say x init equals, we'll say 0.2 now, and we'll say v init equals 0.1, something like this. And we can now substitute x init in here and v init over here. Okay, and now we can have the plot go from minus x init to x init, and we'll need to just copy that. We'll just cut and then put another brace and paste twice, and then we can put a comma in between. So the range of x values it's plotting over are these ones, and the range of v values it's plotting over are these ones. See how that works? Run that again. Might take a little bit longer. I forgot to reduce the amount of time I was simulating for. There we go. So perhaps I need to have twice those values just to make it a little clearer. And I'll simulate for a little bit less time. Let's make it 50 seconds instead. There we go. So you can see that this is now a reasonable depiction of the damping of a simple harmonic oscillator, and I can change my initial conditions. Let's make that 1.2 and let's make that minus 0.5. You can see that regardless of the starting point in phase space, all these trajectories will eventually asymptote to the origin. And incidentally, they will also, none of them will cross each other, which is an interesting fact as well. So that's Euler integration using Mathematica, and you can see that the integration itself has been done with a single line of code. So this is the looping part of the calculation. Sorry, not there, here, this nest list calculation, there we are. This is the nest list calculation, which takes this function and applies it many times. So this is avoiding having to write explicitly a loop. I can use a loop, but this method using nest list is usually to be preferred if we can achieve it.